Hello, today we will learn about element of communication system, receiver. Okay, this topic cover about the frequency conversions, intermediate frequency and image, noise, typical receiver circuits, and receivers and transceiver. For today, we will focus on typical receiver circuit and receiver and transceiver. Okay, what is typical receiver circuit? It includes RF amplifiers, IF amplifiers, AGC automatic gain control, ASC automatic frequency control, and special circuit. Okay, for RF input amplifier, the amplifier also called as a low noise amplifier (LNA) process the very big input signal, increase their amplitude, and do mixing. And these low noise components used to ensure a sufficient high and SN ratio, signal to noise ratio. Selectivity should be such as it effectively to eliminate the image. So this image actually is the noise and we don't want it, so the selectivity is need to eliminate this image. And this RF amplifier is typically a class A circuit that can configure with the bipolar field effects transistor FET. Okay, this is the RF amplifier that used in the receiver front end. Okay, we can see that here have the antenna where the information is received from the antenna, and first we will amplify it with the transformer. Okay, and then we will go to a this one is a LC tune circuit and connect to this is our FET, and here is also the RC filter. Okay, this is our RF amplifier used in the receiver. Now we go to IF amplifier. Most of the gain and selectivity in a super hetero receiver are obtained in IF amplifiers. IF amplifiers are the tuned class A circuits that are capable to provide the gain in the range of 10 to 30 dB. Usually, we have 2 or more IF amplifiers are used to provide the adequate receiver gain. Okay. So this IF amplifier mainly is to provide a better receiver gain. So these ferritic coil transformer are used for the coupling between the stages. And selectivity will be provided by the tuned circuit. Okay, so we can see from the figure here, we have these two, the first one and the second one. These two are the IF transformer, okay, where they are the ferritic coil transformer with used for the coupling effects. Between two stages is this one. The two stages between is IF amplifiers. Okay, so this figure showing two-stage IF amplifier using the tuned transformer coupling for selectivity purpose. It allows us increase the gain. Now we go to the automatic gain control circuit. The receiver gain are far greater than the required for the adequate receptions. And the excessive gain is usually cause the received signal to be distorted and transmitted the information will be less intelligent. Thus, this manual gain control can be achieved by using the potentiometer in the RF and IF stage. And these receivers include the volume control in the audio circuit. These AGC circuits are more effective in handling large signal and give the receiver with a very wide dynamic range. Okay, this is the figure of the IF differentiate amplifiers. Okay, so from here we can see we have two differential amplifier, one Q1 and Q2, and then we have Q3, the amplifiers. Okay, this one they will automatically control our gain. Next, we go to Squirrel Circuit. This Squirrel Circuit actually is a muting circuit found in most of the receiver, which means when we want to mute up the circuit, this switch is used to keep the receiver audio to turn off, which means we mute up the circuit. Like you don't want to listen to my sound, you can mute it up and turn off until the RF signal appear at the receiver input. Okay, so in the AM system, usually we will use for CB radio. The noise level is high, can be very annoying. Okay, the Squirrel Circuit provide a means of keeping the audio amplifier to be turned off. So we are turn off the audio amplifier during the time that the noise is received. So when we are receiving some noise like noise that we don't want, okay, from the background, okay, we can mute it up. And it's also enabling it when the RF signals is appear in the input. So it will appear the wanted signal at the input. Next, we go to the integrated circuit in the receiver. Just now we have the RF amplifier, and AGC as well as the Squirrel Circuit. All these are available in the receiver. And all these circuits, they are built in the receiver, we will known as a IC. Okay, a complete receiver usually is consists of 3 or 4 IC. So we have push the coil, transformer, capacitor, and filter. The modern receiver are contained on a single IC. Okay, the IC actually is integrated circuit. These IC receivers are typically broken down into 3 major sections. The first section is the tuner, which means where we select the frequency, tunes circuit, which tunes the range that we want, and RF amplifier to amplify and selectivity, and the mixer provide the frequency conversions, and local oscillator where generate the frequency for the carrier. Okay. For the second section, we have the IF sections with the amplifiers, which means it's the IF amplifiers, and the demodulator, where we will demodulate the receiver modulated signal. Okay, so after modulate the signal, okay, we will have this as well as AGC, where we'll increase our gain and the selectivity, and also have the muting circuit, which means it's the Squirrel Circuit where we can mute up the audio amplifier. Okay, the last one, third part is the audio power amplifier. Okay, normally the second and the third sections are entirely implemented in a IC, and this tuner may or may be for often the LNA is separated. This LNA, still remember what's that? Okay, if you cannot remember, we can go back the previous slide and have a look. What is LNA? It's a low noise amplifier. Okay, now we continue with a single IF receiver. Okay, the most common that we have is the Motorola MC3363 FM receiver IC chip. It contains all the receiver circuits except for the audio power amplifier. This audio power amplifier is a separate clip and is designed to operate the frequency up to 200 megahertz. Okay, this is widely used in the coilless telephones, cordless telephone, and tagging with the receiver, and also other portable applications. And you can find this mostly in our home telephones where it's cordless. Okay, and this dual conversion receiver contains of 2 mixers and 2 local oscillator and a limiter and a quadrilateral detector, and the Squirrel Circuit. The first local oscillator has built-in the varactors that allow it to control by an external frequency synthesizer. Okay, so we can see this one is the figure of the circuit of the Motorola MC3363, the dual conversion receiver IC. Okay, from here we know that we have the mixer. Okay, the mixer input, and we also have the this one is the base emitter collector for the amplifier. Okay, and we also have a second mixer. Okay, just now you see in here we have two mixer. Okay, so first and the second, and we also have two local oscillator. Okay, two local. This one is the first one, first tank LO. Okay, and the second one, second LO base. Okay, second LO emitter and local. LO is local oscillator base. Okay, second one, and we also have a quadrature detector and squirrel circuit. Inside here we also have limiters. Just now in the explanation we have limiter, quadrature coil. Okay, this part is the quadrature coil. Okay, and this one is the mute input. The squirrel circuit or muting circuit is this part. Okay, this one is our muting circuit. Okay, this one is our squirrel. Okay, this one is our limiter. Okay, and this part is our local oscillator, and we also as well have the control, and we have the mixer, and this part is for our amplifier. Okay, so this is everything inside a IC. Okay, next we will go to receiver and transceiver. Transceiver is a transmitter and receiver both combined. You will get a transceiver. Okay, which means it can receive and also it can transmit the information. Okay, most of the two-way radio communication equipment is packaged, have both transmitter and receiver. So we know it as transceiver. And this transceiver range from large, very high power desktop until very small pocket size handheld unit. Okay, we have a very big unit and we have a very small unit like your handphone, and we have a very big unit like your PC, your very big like as a satellite unit, etc. Okay, and this transceiver have a common housing and the power supply. And transceiver can share the circuit whereby it achieve the cost saving as in some cases are smaller in size. Okay. Now we go to some example on the calculations for this receiver. Okay, first one we will focus on this frequency modulator, the varactor modulator. Okay, for this topic, the question is the value of the capacitor for a reactor at the center of its linear range is 40 picofarads, and this reactor with a parallel with 20 capacitor. So we know that we have a reactor parallel capacitor. Okay, so which means we will have a capacitor 1. Okay, is parallel with capacitor number 2. Okay, this one is 40 picofarad, and this one is 20 picofarad. Okay, then what's the other value of inductance should be used to resonate these combinations to the 5.5 megahertz and its oscillator. Okay, how much should be the inductance value? So first, we know that this capacitor is parallel. So we are using the parallel capacitor value. Total capacitance is equal to your C1 plus with your C2. So we will have 40 plus with 20 picofarad. So total is 60 picofarad. Okay, done. Next step, we know that from here we have our resonance frequency. Our R naught is equals to 5.5 megahertz. Okay, so from here we want to find the inductance value. Okay, so we are using the resonance frequency formula 1 divided by 2 pi LC, LC. Okay, So to find this L, so we have the C value. Okay, we just substitute inside the C value and we can find our L. So we rearrange this equation, we get L equals to 1 divided by 2 pi F, okay, bracket square, and our C total. Then we substitute inside. Okay, L equals to 1 over 2 pi F is 5.5 times 10 power of 6, the whole thing bracket square, and then multiply with our 60 times 10 power of negative 12 picofarads. Okay, so put inside the calculator, we will get 13.97 times 10 power of negative 6 Henry. So it's equal to 14 mil H micro Henry. Okay, because negative 6. Okay, done for this question. Yeah. Then we go to the next questions. Receiver sensitivity. To find the receiver sensitivity from the questions, we have the receiver and have an antenna. Input impedance is 50. So our input impedance ZI or RI is 50. If the input sensitivity is 10 micro voltage and find the sensitivity above 1 milliwatt. Okay. First, we know that 1 mil V, our micro voltage signal produce how much of the power? Okay, so how much? So what we do is we're using the formula P equals to V squared over R. Okay, so we have our V is 1 times 10 negative 6 divided by 50. So which means at the signal of 1 times 10 power of negative 6 to go through the R, this resistance, the impedance, input impedance R is 50. So we divide, we know that 1 mu V, we have 2 times 10 power of negative 14 watts. Okay, done. Next, we have to express this one in 1 milliwatts. Reference the power, reference to 1 milliwatts. Okay, so we are using the formula 10 log our power divided by 1 milliwatt. So is equal to 10 log. Your P is 2 times 10 power of negative 14. Okay, divided by 0.001. Okay, 10 log of this reading. Here I have 10 log. So it's 10 log of this reading. So we will get negative 107 dBm. Okay, done. Then we go for continue. So just now the question said the input sensitivity is 10 micro voltage. Okay, so just now we found 1 micro voltage already. Now you want to find 10 micro voltage. So 10 micro voltage is equal to 20 log 10. So we have 20 dB. Why are we using 20 here? Because it is in voltage. Okay, 20 dB. Then the sensitivity above 1 milliwatt is 20 minus of 107, we will get negative 87 in dBm. Okay, so this one is our answer. So we found out at this range, the sensitivity above 1 milliwatt is negative 87 dBm. Okay, now we go to the third example. Okay, this example is the receiver for the frequency conversions. Okay, frequency conversion. Suppose a local oscillator frequency is needed that it will produce the IF, intermediate frequency, of 70 megahertz for a signal frequency of 880 megahertz. What are the possible values for this oscillator frequency? Okay, so I want to find the possible value for this oscillator frequency. So now it produces the IF is 70 megahertz. Okay, from this signal. Okay, so what we do? So we know that our this frequency also refer back these frequency conversions. Okay, we have a mixer output F0 plus Fs, F0 minus Fs, F0 star and Fs. And this IF is equal to F0 plus Fs will be equal IF, and F0 minus Fs will be equal IF. Okay, so in order to find our F0 actually is the frequency generated by the local oscillator. So we can equal F0. So bring over here, we will have IF minus of our Fs or IF plus Fs. So F0 is equal to Fs plus Fif. So we will have 880 plus 70. So we have 950 megahertz. And also another is Fs minus of Fif, 800 minus of 70. So we have 810 megahertz. That's all for today. Thank you. And remember to subscribe my channel. And thank you. Bye.